Alrighty. So my name is Christina Jones. I'm presenting on behalf of myself and my faculty advisor, Dr. Mahmoud Sharara from NC State University. And today I'll be talking about the impacts of flush water nitrification on the mesophilic anaerobic digestion of swine manure. This is particular to the southeastern United States, North Carolina specifically. And I say that because manure management in the Midwest, where most hog production tends to occur, is a bit different than that in North Carolina, how we're testing the system. So in the Midwest, you have a deep pit. It collects manure throughout the year, as well as some amount of wash water. And then about once or twice a year, you empty that out and you spread it on cropland. In North Carolina, however, you have a much more shallow pit that's emptied anywhere from multiple times a day, maybe once a month. And this is through a flush system or a pull plug, similar to a toilet in many ways. Um, so with that, there's quite a lot of emissions that can occur in these sorts of situations, particularly ammonia. This often results when excessive ammonia builds up in the barns and a decline in productivity, so weight gain, an increase to mortality and disease risk, and obviously lower air and water quality. But particular to this study, as ammonia starts to build up within a digester, you can also see it become inhibited. So to address all of these issues, we have partnered with a wastewater treatment firm for Virginia, and they have produced a nitrification system called Panoxic. This converts up to 90% of the ammonia and ammonium present in flush water to nitrates and nitrites. This also lowers the pH, so anything remaining is less likely to be emitted. As a result of this, you see about 60% less ammonia on site. And you often see a improvement to not just mortality and disease risk, but as well as productivity. I think it's like 2 weeks shorter time, residence time. So we presented this at AIM last year, but typically in a 6,000 head farm, it's projected to receive about 28% more net revenue than a farm without this nitrification system outfitted. And in a 12,000 head farm, we see about a 39% increase. This is a relative benefit of about $250,000 to $480,000. It's important to note, though, that this does not include anaerobic digestion, as it's a bit more difficult to find in literature at the moment, which brings us to our goal today. What are the impacts of nitrification of this flush water on anaerobic digestion? And beyond that, given that there's a variable rate of organic loading into these reactors, based on the age of the hogs, the number in a given barn, what is the impact of organic loading? And when I say performance, I'm talking mostly about biogas productivity, typically in the form of methane, as well as its co-product CO2. And then on top of that, how much of that carbon is actually being digested and converted to biogas, volatile solids, and COD. Beyond that, we're worried about process stability. The ratio of volatile fatty acids to buffer capacity, as alkalinity, is referred to as a Ripley ratio. Anything below 40% volatile fatty acids to buffer capacity is considered to be a stable reactor in the long term. So getting into our materials and methods, we started by sampling at a 6,000 head swine farm in Duplin County, North Carolina. The lagoon is situated in a parallel setup with all 5 barns, and they all flow to one centralized collection box. From there, the manure is pumped into a digester. It drains via gravity to a lagoon, and then the cycle essentially repeats. Panoxic, that nitrification system I referred to, is in loop with 3 of the 5, with the other 2 serving as a control. It's not quite at steady state yet, so we opted to produce a sort of stand-in for a nitrified flush manure. And so we sampled manure and hog urine from the collection box from the control houses, and the nitrified flush water from the effluent of the Panoxic unit. From there, we took our 3 fluids, did absolutely nothing essentially in terms of pre-treatment to our nitrified flush water and urine. And to the flush manure, we wanted to separate the solids out from the control flush water and urine. So we essentially decanted it for a couple days, removed any floating solids, and then extracted any fluid on top of the solid layer. This is referred to as liquid fraction. This is about 1% solids, maybe 0.5. The remaining pool was then macerated and filtered to 1 millimeter to remove any grit or large solids that may not be easily digested. As in a real world scenario, they would tend to sink to the bottom of the sump. Those are discarded. And then the remaining, the filtrate, about 5 to 10% solids, is what we actually use to produce our feedstocks. All of these were characterized for the volatile solids concentrations, and then we standardized them to one of two OLRs. We had, um, oh, I'm sorry, excuse me. The inoculum for each of our reactors, apologies, was sourced from 3 anaerobic digesters, 1 wastewater treatment plant in Southern Virginia, and then 2 swine farms in Duplin County, North Carolina. All 3 of these were used to seed 2 seed reactors, about 12.5 liters total volume. And they were started up over the course of 55 days. Due to labor constraints and some issues sampling, we opted for a synthetic manure blend. This is a mixture of sucrose and minerals that kind of mimic the chemical composition of a standard manure. And then after a while, we started to transition to swine manure. We started at a 1-to-1 ratio to ensure that the reactors could acclimate to more complex carbon. And then from there, we just continued to feed manure. At this point, it was standardized to 4% total solids for an OLR ranging between 1.3 to 1.6 grams of volatile solids per liter of our reactors total per day. From there, we could begin our study. Oh, yeah, no, you're fine. So in terms of our actual treatments here, we had 8 reactors total, 4 classes. We had 2 OLRs. We had the low end being about the 25th percentile of mesophilic digestion for swine manure, 1 gram of volatile solids per liter per day. And on the high end, we had the 75th percentile, about 2. For each of those, we had a controlled and a nitrified feedstock being fed to 2 reactors. From there, we incubated everything at 35 degrees Celsius and fed at a hydraulic retention time or a turnover time about 17 days. And we fed 6 days a week. So there was 1 day off for residual material to kind of burn off. Looking to the reactor system itself, it is funnel fed and via liquid displacement, digestate is automatically discharged out of the discharge pipe. It is agitated via an overhead motor at about 110 RPM, 1 of every 5 minutes. Gas automatically will flow through the system to a sodium hydroxide scrubber, removing any impurities such as hydrogen sulfide, as well as CO2. And all of the remaining methane goes to a gas flow cell for direct quantification. Looking at our timeline of events for the actual experiment itself, we wanted to take our standardized inoculum and let the organic material burn off gradually. It took about 4 days or so before it stabilized, and then we started feeding. For the first HRT, we went with purely control feedstocks, just to allow them to acclimate to their new HRT. And then from there, day 21 or so, we started feeding our nitrified feedstocks to the treatment reactors. This continued until day 55, roughly. And throughout this entire period, all of our feedstocks were prepared every 2 weeks. But we started to notice the potential for denitrification of our feedstocks occurring in storage. So from there, for the next remaining 25 days or so of the study, we produced feedstock daily. After day 81 or so, we decommissioned everything. So we just stopped feeding and let the ultimate biomethane yield kind of reveal itself to us. Getting into our actual results. Here are the average daily biomethane yields. This is taken across 20 hours for consistency. It did range between 18 and 24 hours. At this 20-hour mark, we can see a couple of things. First and foremost, at a lower OLR, you have a higher specific biogas yield per gram volatile solids. And this is to be expected to some extent, given that we're not overloading the reactor potentially. Beyond that, we can see about a 10% higher yield in our control low compared to our treatment low reactors. Moving into our effect of our weekdays on the biogas yields. Again, we only fed it 6 days a week. We allowed it to kind of fast on Sundays, and that allowed for a lot of residual material to burn off, particularly in the lower OLR reactors. It tends to pick up quite quickly. By Wednesday or Thursday, it tends to stabilize. And there's no significant differences between our control and our treatment, but it does seem to be more pronounced, at least, in a lower OLR. Getting into carbon reduction, we can see relatively consistent reductions between our control and treatment within OLRs, but the low tends to be a little bit higher than the high, and that is statistically significant. And we also see a slightly lower carbon content or volatile solids content in our treatment high compared to the control high. This could potentially be a effect of the denitrification and storage we were concerned about. We're still talking to a statistician about how to analyze that. COD reduction similarly has similar impacts, very similar reduction, similar sort of content comparative. And again, you see a little bit higher in the lower OLR compared to the high. Here we have a summary of our results so far. There's a couple of new things, so I'll just cover those. First and foremost, that ratio of volatile fatty acids to alkalinity in the reactor is about 0.24 to 0.3, roughly. It remains that way pretty consistently across the entire experiment, meaning we're not particularly concerned about acidification and souring of our reactors. Additionally, we see similar to COD in volatile solids, our CO2 concentrations are very consistent between the control and treatment, only really differing based on OLR. To conclude, our reactors maintain stability throughout the entire period, and we expect it to continue onward essentially like that. We also saw a significant negative effect of our nitrification at a lower OLR. One in this case could be considered to be underfed in some situations. Beyond that, we see essentially no effect of our nitrification treatment at a higher OLR. And beyond that, COD, volatile solids, and CO2 concentrations are only significantly impacted by OLR. Just want to take a moment to thank Dr. Jay Chang and Kelly Ziering at NC State, the many undergraduate assistants that helped out with this project, and our industry partners.